Hi, and welcome to Indian Nanoelectronics User Program at CNNP IT Madras. I'm Bhaskar, and I'm from the INUP team at CNNP IT Madras. And in this talk, we'll talk about the wafer cleaning process in semiconductor manufacturing technologies. So here is the outline of my talk, which includes first the importance of wafer cleaning, where I'll talk about why this wafer cleaning step is so important in order to have a very good device performance and yield. Next, I'll talk about the objective of wafer cleaning, where I'll explain that what are the things that we aim to achieve by doing this extensive cleaning using this standard recipes of so cleaning solutions and all that. Next is the wafer cleaning step itself, the protocol that is typically used in industry and academics. Next, I'll describe a reference that is very good for learning in detail about all this wafer cleaning steps and processes. So let's move on and start with the importance of wafer cleaning. Now, the question that we ask is, why is cleanliness so important? Why do we why do we why do we give so much amount of time and effort for such a clean environment, such as clean rooms and such a clean silicon wafers? And the answer to that question is the device performance, reliability, and product yield is critically affected by the presence of impurities. And all these impurities play a very important role in deciding which devices will be working and which devices will not be working, and what will be the performance of such devices, especially for the field defect devices. And these devices are extremely sensitive, especially for the surface, because of the planar technology, planar device technologies. This semiconductor surface is very much important. And since we are imprinting nanometer size features on the surface, it's extremely important to have a ultra clean semiconductor surface so that the devices are working and your chips give a very good result. So in that case, an ultra clean silicon wafers are required. It has been estimated that about 50% of the yield loss in IC manufacturing is caused by the microcontamination, that is the contamination of the silicon surface. And this is why we give so much amount of time and effort for the cleanness of our wafers. And so let's proceed with the slides. So we saw that why the cleanliness is so important, but what are the quantitative estimation? What are the quantitative parts so that we can decide that how much clean we want our surface to be? Now, cleanliness is a very subjective terms for you. In that case, for your home, it can be clean. You can make your home super clean, and still want to be clean from the semiconductor standard. What we require is an ultra clean atmosphere and ultra clean samples, and then we must quantify this clean term that we are using. So ITRS is a body that is international technology for roadmap of semiconductors. So it decides the metrics that is involved in deciding this all these factors. So for the technology node that is at 2017, it gave a metric that the total metallic impurities should be less than about 0.5 into 10 to the power 10 atoms per centimeter square. Now this is extremely important because per centimeter square normally silicon has about 10 to the power 22 atoms. So we can guess that how much of this matrix is that we want to less than one impurity in 10 to the power 10 and the power 12 atoms. Apart from that, the particle size should not be, that is a particle size which is larger than the pitch of the smallest dimensions that are fabricated on a chip, should not be larger than 0.1 per centimeters. Now this translates to less than 30 such particles per 300 millimeter wafer. That is, if you have a 300 millimeter wafer, then there will be less than 30 uh, uh, such particles. That is the standard of the cleanliness that we're talking about. And due to this, about 15 to 20% of the process steps are the cleaning steps. And that is about 1/5 of the process steps are cleaning steps. Usually, we decide the cleanliness of a room by a metric called class of a clean room. And we designate it with the numbers such as from 1 to 10 lakh, meaning the number of particles that is greater than zero point 0.5 micron in a cubic feet of air. For example, if the class is like 1,000, then there is no then the maximum number of particles that can be present, which is greater than 0.5 micrometer in a cubic foot of air, is 1,000, and there could be no more than that. For comparison, a typical office building is about class 1 lakh. That is about 1 lakh particles of 0.5 micrometer is present in a typical cubic feet of air and in your office. And also for comparison, a typical person a typical person emits about 5 to 10 million particles per minute. So we can see that the greatest source of impurities is actually a person that is working in the lab. So that's why we use the bunny suits and all these protocols for dressing ourselves and then cleaning ourselves with the nitrogen air gun, so that we can reduce the number of particles contaminants that are present on us and that we emit in the lab. So in order to access the importance of the cleanliness, here is the total number of steps that are there for cleaning, that is there in the technology note of 2017, that is a 14 nanometer IC technology note. You can see that there is a total of 119 such steps that are dedicated to just the cleanings. This BEOL and FEOL refers to the back end of the line and the front end of the line processes. The front end of the lines typically are the processes that are in the initial stages of application, such as where silicon oxide and silicon nitrides are present. While the back end of the line processes are the processes where after the metallization, that is where the interconnects and all has been laid down. So you can see that huge number of processes are typically involved in cleaning. Now let us see what are the objectives of a wafer cleaning and what do we try to achieve when we are doing this wafer cleaning. Now, of course, one of the primary objective is to remove the impurities from the semiconductor surface, those that are particularly very detrimental to the performance. But what's important is that they must remove these impurities without damaging the surface. Because as we will see that the solutions that we employ are chemicals, and those are strong oxidizing agents, strong acids. And as such, as they remove the impurities, they also damage the surface in a way, some less than the other. But of course, there is some damage, and these damages are seen as a surface roughness or pitting or a corrosion. So we try to minimize this damage while we employ these solutions for removal of the particles and contaminants. And the other point is the surface conditioning, which needs some clarification. Not only apart from cleaning the silicon surface, solutions also prepare the surface for the next step chemically. And this is important because, for example, when we are doing the HF dip of a sample, then it removes the oxide. But not only it removes the oxide, it passivates the surface with HF. That is a prerequisite when we are doing epitaxial deposition after that. So the surface conditioning is actually preparing the surface for a next step in a favorable outcome. For example, we can do some solution that is good at cleaning, but If it doesn't prepare it for the next solution and it is actually detrimental for that, then we have to avoid using such a solution. Now we'll see what are the different contaminants that are present and what are the effect of the contaminants that is there in the next slide. Let us now look at the types of contaminants that are common in silicon processing and their effects on the performance of the devices. Now, this will be a brief discussion, not an extensive one, and I'll just briefly allude what these contaminants are and where these contaminants come from and what are their typical effects on the performance of the devices. So broadly, the contaminants can be divided into three categories. That is the organic, no, the sorry, the molecular compounds, the ionic, and the atomic species. Molecular compounds that are mostly particles or films or condensed organic vapors that from lubricants, grease, or photoresist or solvent residues, and and they can also come from like prior processing steps like photolithography or from human contacts. These organic compounds can also come from DI water, from fingerprint, or from even from plastic storage boxes that we use for storing the samples. The other is the ionic materials, that is the ionic species, that is the cations and the anions, which are mostly from inorganic compounds that may be physically adsorbed or chemically bonded, such as the lithium or sorry, such as the sodium or the fluorine ions or like the potassium ions. And the other group of contaminants are the heavy metals, which are the copper, nickel, or cobalt, etc., that are particularly detrimental for the device performances. There are also metal residues that can come from the acids or the solvents that we use. These are typically the contaminants that are present in these acids and organic solvents, and they also can also come from the tweezers that we use to handle the vapors. There is dirt and dust that can come from like dicing or sawing or the storage boxes that we keep in, or from human contact, or from even the atmosphere of the supposedly clean room, which of course is not perfect, and still there can be some impurities. There's also the native oxide that is formed, which is not very pure when we expose the silicon vapor to the ambient air, and this ambient air may contain, for instance, metal particles for instance, metal debris from some equipment, and this can contaminate the surface of the silicon vapor. Now, the question is that what are the effects of these contaminants on the performance of the devices that we get? Particularly the molecular contaminants, that is the molecular components that act as a mask, preventing the effective cleaning and rinsing of the silicon samples, hindering any good adhesion of the deposited films. Also, the ionic contaminants, for example, when they are subjected to a high temperature or to an electric field, they diffuse to the silicon core, the silicon bulk, and they spread to the surface, and they lead to this electrical defects, device degradation, and yield loss, to name a few. These contaminants also decrease the rates of the oxidation and the oxide quality that we uh, that we try to achieve for such samples. The quality of the oxides would be very good. Otherwise, there would be drastic shifts in threshold voltage, and that will not be predictable. And this is also evident from the behavior of the contaminants, such as the alkali metal ions, and those metal ions are mobiles, and they move inside the bulk of the silicon when a wheel voltage is applied, and as such they cause a random fluctuations in the threshold voltage. leading to a very drastic and unpredictable behavior, and thus causing reliability and problems. These heavy metals are particularly very detrimental because these heavy metals introduce energy levels in the forbidden energy gap and introduce traps and recombination centers, and that reduce the carrier lifetimes and change the surface recombination velocities, and thus also lead to hot carrier degradation effects and shifts of the threshold voltages. So we'll see how these contaminants are dealt with in a sequence of recipes that will explain in the upcoming slides. Okay, so now we move to the wafer cleaning step, and we'll see what are the different types of uh, cleaning that is used in the semiconductor fabrication industry. So the first is the aqueous chemical process that is based on the aqueous based chemistry, which typically use hydrogen peroxide mixtures. On the other hand, there is also plasma processing and vapor based or other dry cleaning methods, which are normally used for back end of the line process where there is a need to clean the deep level interconnects that where the aqueous based chemistries are not particularly effective. But still today, about 70% of all the cleaning steps are based on aqueous chemistry. So the the importance of these cannot be overemphasized. So what are the different aqueous-based solutions that are used in the semiconductor industry? And we'll look at it one by one. So first is the Pinano solution, which is a mixture of sulfuric acid and hydrogen peroxide in the ratio 3:1. That is, we add 3 part sulfuric acid and 1 part hydrogen peroxide by volume. And this is also called the sulfuric acid peroxide mixture. This solution is highly exothermic, as is implied by the name Pirhana, and it's voracious and just strips away all the organics and the organic contaminants from the surface of the silicon wafer. But the downside of this process is that it leaves the surface roughened, that it creates a much more surface roughness that is usually uh, done by the normal degreasing procedure to remove the organic contaminants. So we resort to that only when the normal degreasing does not work. For instance, when in the cases where, for instance, we do some processing steps and the photoresist has been hardened and it's not getting removed by the acetone, or in cases where the silicon sample is visibly very much uh, organic impurities are present that is not usually being removed by the normal degreasing procedures. The second is the degreasing. That is, degreasing is used for removing the organic contaminants. And this process is done by dipping the solution in organic solvents such as trichloroethylene for 2 minutes at boiling temperatures. Once we do the TCE dip for 2 minutes, we then immediately move the sample to acetone and then at the boiling temperature. So acetone dissolves the organic contaminants, but leaves behind the residues that is removed by the IPA that follows. So after removing from the acetone, we dip in IPA at room temperature to remove the acetone residues. We then typically perform boiling nitric acid dip, where we dip the samples in boiling nitric acid to oxidize it and then remove the oxide layer by using HF. The HF removes the oxide layer by using the etchant ion, that is the fluorine ions. This F minus is the ion that removes the oxide layer. Now, there is also a standard cleaning procedure, that is the RCA1 and the RCA2, which is more standard in removing the organics and the metal ions. Uh, Now, these are the standard protocols that has been developed at the Radio Corporation of America, and is what followed for the better efficiency and It gives a very good results and is very effective in removing all the contaminants. We'll look at it in the next slide in detail about what the RCA1 and RCA2 is and what are the solutions that are employed in this. Once we perform the RCA1 and RCA2 solutions, or solution clean, then there is an oxide layer that is left after the RCA2 step that is typically removed with the HF, dilute HF solution, that is in 1 part hydrofluoric acid and 50 part DI water by volume. Or the buffered hydrofluoric acid where the etchant F minus is buffered by NH4F that provides the HF2 minus as the etchant species, which is the oxide layer. So in the next slide, we'll see what the RCA1 and RCA2 solution is in detail. So now let's move on to the standard cleaning protocol that is developed at the Radio Corporation of America in 1964 and is published in 1970. This is called the RCA cleaning protocol, and it consists of two consecutively applied hot solutions, especially formulated to remove the prominent contaminants that are present in silicon manufacturing technology. Now, these solutions are called the standard cleaning 1 and the standard cleaning 2 solutions, also commonly referred to as the RCA1 and the RCA2 solutions. These are actually peroxide mixtures. The recipe that I've written here is that of the original published work, and since then has done some modifications in order to accommodate the need for controlled cleaning procedures. So here I will discuss the original sequence that is still very commonly used in the industry. So the SC1 or the RCA1 consists of a mixture of ammonium hydroxide, hydrogen peroxide, and DI water. The originally specified ratio for this is taken to be 5:1:1 to 7:2:1 parts by volume of the DI water, hydrogen peroxide, and the ammonium hydroxide. That is, you take 5 parts DI water and then you mix 1 part hydrogen peroxide and then you mix 1 part ammonium hydroxide. The commonly used ratio is 5:1:1. The hydrogen peroxide and the NH4OH that is used in the RCA1 solution is of very high purity, that is of the electronic grade, and the H2O2 is unstabilized, that is without any stabilizers. The temperature specified for this solution is 80 degrees Celsius to 90 degrees Celsius, and the duration is from 10 to 20 minutes. Immediately after the RCA1 is performed, we take out our sample and then we do a DI water rinse. And then we move the sample to the RCA2 solutions, which consists of a mixture of hydrochloric acid, hydrogen peroxide, and DI water. The specified ratio for the RCA2 is 6:1:1 to 8:2:1 parts by volume of H2O, H2O2, and HCl. That is, we take 6 part DI water and then we mix 1 part hydrogen peroxide and then we mix 1 part hydrochloric acid. The concentration of the hydrochloric acid is 37%. The temperature specified for this is 80 degrees Celsius to 90 degrees Celsius, and the duration is 10 to 20 minutes. Now, in the next slide, we'll see that how these solutions actually work in order to clean the silicon samples. Immediately after we perform the RCA2, we move the solutions for DI water rinse and then nitrogen dry. Now let us see how the RCA1 and the RCA2 works for cleaning the contaminants that are present in the silicon samples. Well, the RCA1 consists of ammonium hydroxide and hydrogen peroxide mixture, in which case the hydrogen peroxide is acting as an oxidizing agent, and the ammonium hydroxide is acting as a solvating agent, which purpose is to wet the surface so that the contaminants are removed and and the contaminants are actually dissolved in the solution itself. The way the RCA1 works is by forming complexes with periodic group elements such as 1B and 2B in metals, such as copper, gold, silver, and zinc. It also forms amine complex with other group elements like nickel and cobalt, etc. So before the advent of atomic force microscopy, it was not known how the RCA1 actually cleans the surface of the wafer. And after the discovery of AFM, we realized that the way RCA1 works is that it dissolves the thin native oxide of the silicon that is present at a very low rate, and it forms the new oxide at approximately the same rate. So as such, the impurities that are contained in the oxide is removed, and after the SCA1 is performed, we have a freshly made oxide layer that is present on the sample. So after the SC1, because of the presence of the oxide layer that is very thin, the surface is hydrophilic. Now, as mentioned in the previous slide, after removing from SC1 solution, we rinse the samples with DI water, and then we place the samples in SC2 solutions, which consist of the hydrogen peroxide and hydrochloric acid mixture. So the way SC2 works is that it removes the alkali residues that is left behind after the SC1 solution, and any residual trace metals like silver and the gold, which are very detrimental for the performance of the device because it introduces traps, which causes threshold voltage shifts due to the recombination information carriers and modification of the surface recombination velocities. Now it also attacks the metal hydroxides and removes it, but it does not have the oxidation property of the SC1, and it does not etch the Si or the SiO2. However, SC2 has a better thermal stability than SC1. Now it has been noticed that the SC1 causes more surface roughness than the SC2. And in that case, we can reduce the surface roughness by reducing the hydrogen peroxide concentration. And these are the modifications that has been employed recently in the industry. By diluting the concentration, we can actually reduce the surface roughness, and it performs a much better device fabrications results. So we'll see in detail that how this sequence is performed in the next slide. So let us recapitulate what we have learned so far. So as mentioned in the earlier slide, we start with decreasing, which is the removal of organic contaminants, which involves a sequence of TCE, then acetone, then IPA, then DI water. Now, after decreasing, we go for HNO3. That is, we dip the sample in HNO3 at a slightly elevated temperature, which may be around 35 to 40 degrees Celsius. And then we do dilute HF treatment of the wafer. Apart from that, if the surface is visibly contaminated and if there is a hardened photoresist or something, then we do piranha, which is a sulfuric peroxide mixture. So we can also do that in case of decreasing in those cases. So after the HF treatment, we do the DI water rinse, and then we treat the sample with SC1 solution or RCA1 solution. The ratio of 5:1:1, where the 5 parts is for DI water. And as alluded to earlier, in order to reduce the surface roughness, we can go for a lesser NH4OH concentration also in SC1. So once we treat the sample with SC1, then we do a DI water rinse, and then we treat them with SC2 solution, which is in the ratio of 6:1:1, where 6 part is DI water. And then we do a DI water rinse. And then, as I mentioned, that after SC1, there is a oxidized surface. So you can see that after the SC1 treatment, the sample will be hydrophilic. So SC2 also does not oxidize the surface, so there is no changes. It does not remove the oxide from the SC1, so there is no changes in SC2. So after SC2 treatment, the surface will still be hydrophilic. But after DI water rinse, when we treat the sample with a final dilute HF solution, then the oxide layer will be stripped off and the surface will become hydrophobic. And that is where we can identify that there is no oxide on the sample and the surface is visibly very clean. Okay, so that's the sequence for the standard RCA cleaning. If you want to learn any further, delve deeper into this, then I recommend you this book, which is by Kern, who is the one who developed this protocol. So it's a very good book where you can learn, all the intricacies of wafer cleaning that is used in silicon cleaning technologies. Okay, so next video will be a hands-on video of silicon wafer cleaning. So